Welcome back, ladies and gentlemen. In this video, we'll be talking about stress energy momentum tensor for a perfect fluid. Stress energy momentum for a perfect fluid. You must be aware that in the previous video, I've talked about the contents of stress energy momentum tensor from the point of view of a linear symmetric machine, and we have seen how to understand different parts of the stress tensor. And if you haven't seen it, I'll be linking that video somewhere. Right now it should be appearing. So if you are not in a hurry, go back and watch that video and then come back. Then these things will make much more sense. Provided that you have seen it or you are familiar with the initial understanding of stress tensor, I will now resume our discussion of the stress tensor for a perfect fluid. The stress energy momentum tensor is very useful in a lot of contexts, but for a perfect fluid, this is particularly useful in the discussion of cosmology. Particularly if we are studying the evolution of the universe from a general relativistic point of view, then this is very, very important. So the first question that should come up in your mind is, what is a perfect fluid? So obviously this has something to do with fluid, but how do we know that it is perfect? So a perfect fluid must have two characteristics, right? Number one, obviously it's a bunch of particles, right? So that means a perfect fluid is a collection of particles, or I'd rather say gas or liquid. So that's what fluid means, but it's an idealized version of it. So a collection of particles cells is just as fine. But what do they do? In this case, we're sort of we are ignoring the interaction among them. So the stickiness, which is a property of a lot of fluid, we're going to ignore that. So they are interacting, but interacting by means of exerting pressure on itself. And that pressure has a peculiar property in its rest frame. So that's very important. So first thing we'd like to do is to draw a figure in order to sort of make a point. And so here we have a bunch of particles, which will be a perfect fluid. How? So there will be associated velocities, right? Pick one. So let's pick this one. It has a full velocity u. So let's assume this particle momentarily stays at p. So its velocity will be u at p, right? Of course, this velocity is going to vary from point to point. If this is at point Q, this would be u at Q, and this can be totally different from u of p here. So at each point assigned to each particle, there is an associated full velocity that can vary from point to point. So that is our first criterion. Its mass energy density is going to be rho. That can also change from point to point, and this exerts a pressure. And if we look at the rest frame of any fluid element, that pressure is going to be isotropic. So number one, it is characterized by the velocity u, which is dependent on different events of space-time, and number two, in the rest frame, there is the characteristic mass energy density rho, and isotropic pressure P. So what do we have? At each event, we have the following things. So first, obviously, we have a metric tensor, right? So the metric tensor is defined as follows. So G, mu, nu, these are the components, and then we have dx mu tensor product with dx nu. So this is how the metric tensor is written in its full form. Notice that it is a geometric object. It is essentially a 0-2 tensor. It has two slots. The first slot, you can insert a vector, which is going to be acting with this one form here, and you can also plug in another vector, and that will be acting with this one here, and overall two inserted vectors will produce a number. So that's why it is a 0-2 tensor. So we have the metric tensor defined everywhere at every event of the spacetime. We have the one form, which is U, associated with the fluid. So remember, we characterized the fluid by the full velocity at different events. So, and that was also denoted by U. Now, this one form U is obviously related with that full velocity, which is the characteristic of the fluid at each event. And precisely, as geometric objects, they contain the same amount of information. But this is a one form, and that U was a vector. It's a full velocity, it's a full vector. This is a one form in 4 dimension, and the way they are related is that we take a flat operation on the vector, and we know that flat of a vector, which is a musical isomorphism, gives us a corresponding one form, and that is this one form here. So this is the one form that stems from the full velocity of the fluid. So one form associated with the full velocity, right, of the fluid. And this is also defined at every point or every particle of the fluid. And then we have rho, which is the rest frame density of the fluid, right? And we also have P, which is the isotropic rest frame pressure, right, associated with the fluid. So these are the things that we have. And the stress energy tensor for a perfect fluid is written as this. So T, as a geometric object, is equal to rho plus P, and this is the coefficient of the tensor product of the one form associated with a full velocity. So, so this is symmetric, right? One of the criteria that was imposed on T. Plus, we also have another component, which is P multiplied with the metric tensor of that space. And in terms of component, what is it going to be? So T is going to be rho plus P, and then we have U alpha U beta plus P multiplied with G alpha beta. Now, this makes it enormously easier for us to study different components of it. So, at the very beginning, what we're going to do is to contract it with a vector. So this is the same as plugging in a vector into one of the slots of the stress tensor. So we insert here the associated full velocity. So what is it going to give us? we have rho plus p, then we have ub, and then we have u alpha plus p g alpha beta, and then we have u alpha. So obviously we have u alpha. This is precisely the magnitude of the full velocity of a particle, and we know that p alpha is equal to negative m squared, and this quantity here is precisely this quantity divided by m squared, so this is going to be -1. So what we have is negative rho, negative p, and from here, this object from this contraction gives us u of beta. So we have this multiplied with u of beta plus p u of beta. So we can clearly see what we get here. This is simply negative rho u beta, negative p u beta plus pressure times u beta. Obviously this cancels this one, and all that remains is negative rho times u beta. Now, this thing here, where we have T alpha beta u alpha equal to negative rho times u of beta, this is a fantastic result. Why? Because, let's say, I want to find out T alpha 0 and then u alpha, and this would be given by negative rho times u 0. And we do know the zeroth component of the full velocity is c, and in our context c is equal to 1, so this is simply negative rho, which is the mass energy density, which can also be written as dp0 dv, which is also the zeroth component of the momentum density. So that's that. What do we get if we plug in a space index here, so u alpha? We get negative rho multiplied with uj, but in the rest frame uj is equal to 0, so this is going to be 0, and this was the momentum density, remember, which was negative dp j dv, and for a set of non-interacting particles the momentum density is 0 in its rest frame, and that's also an intuitive result. What else do we have? We have t, then ij, and judging from this is going to be p times delta ij, and of course this is the component of the stress tensor. So in the rest frame, if we want to enlist these things in the form of a matrix, we get negative rho and then p, and the rest of it, and the rest of the components are going to be 0. Right? Here should be a 0, 0, 0. Right. So that's that. This is what the stress energy momentum tensor looks like for a perfect fluid.